All right, welcome to the networking session. My name is Chenren Xu from Peking University. I'm the chair for this session. And in this session, we will have three very exciting talks, cover from the low-level IoT protocol to cellular infrastructure to all the way to the network applications. Our first presenter will be Alex Ballon, who is a second-year PhD student at UC San Diego, where their research focus on the intersection of security and mobile systems. They will be talking about TagAlong, a free wide area data muling service built on the AirTag protocol. Okay.
Cool. Thank you. Let me get started here. Hi, my name is Alex, and as Chenren said, I'll be talking about our work TagAlong, a free wide area data muling service built on the AirTag protocol. So let's start out with a hypothetical situation. Say we wanted to measure how many people were using a computer lab, and we wanted to put a sensor on each chair to detect whether or not people were in there sitting in the chairs. And normally, if we wanted to deploy a sensor, this would also involve a lot of infrastructure deployment. So, we would have to either connect each sensor to the internet, or we would have to set up gateways, all of this to provide infrastructure, a backhaul network to send our data back to a central location. And so this would be a good situation to use data muling, using other existing devices to carry the data for us from the sensors back to our central location. And our work TagAlong is going to enable that for free using existing infrastructure. So let's talk a little bit about AirTags, which kind of use data muling, in their normal functionality. So when you first pair an AirTag with your owning device, there is a private and public key pair that are generated, as well as a symmetric key. And combined, these are referred to as the master beacon key. And this master beacon key is synced between all your devices so that, it's synced between all your devices. And the way that the private and public key are used is that AirTags broadcast out these public keys that are generated with a key derivation function starting from that initial public-private key pair. You can derive the next set of public keys, and the public keys are changing on a rolling basis every 15 minutes. And so 15 minutes later, you have a new public key that looks random, but it's deterministically generated. And you will continue every 15 minutes changing the public key until eventually an iPhone will pick up one of these public key advertisements, and using this public key, they will use their own GPS location, so there's no GPS on a normal AirTag. It's all from the devices that pick up these Bluetooth advertisements. They'll take their GPS location, encrypt their location, and generate what's called this location report, which will then be uploaded to Apple servers. And so on Apple servers, this is kind of what it looks like, where we have the public key associated with the location report. And there's tons of these public key location report pairs, and when you want to find your device, your owning device will send a request for this public key, and then the server will find the associated location report, return it to you. You can decrypt it and get the location of your AirTag. So some prior work, Senmai, was able to use this to exfiltrate one bit of arbitrary data at a time, and that was by changing what was in the public key to encode data using this encoding scheme. There were some limitations to this, though, where we only had one bit of data per Bluetooth advertisement packet. Only one byte of the payload was being used for actual data. There was a lot of padding. And again, with all of these IDs, there was naturally an upper bound on how many modems or messages you could have, because you could overflow the integer. And so going back to our hypothetical example, we kind of want to think about what primitives will we want in this situation. We want an unlimited number of messages, modems, data, increased data rate more than just 1 bit per advertisement, and a greater payload size. And so that's what TagAlong enables. We provide scalable arbitrary data transmission using the existing FindMy network. So we use existing FindMy infrastructure to remove the limits on the number of messages, modems, et cetera, that Senmai had. We have variable payload sizes to accommodate different situations, which we'll talk about later. And we have a more efficient use of the Bluetooth advertisement packet. So going into each point, the first one is we use existing FindMy infrastructure to remove limits on messages, modems, and bit lengths. And so instead of having an ID number to identify which number message this is, we will use this list of rolling public keys that's predetermined to signal when we have a new message. And that will get rid of the limit on messages, because there's no hard-coded ID number, Instead, you can just continue through this key derivation function and keep generating new keys. Additionally, because this progression of public keys is unique to each tag device and owning device pair, that will help you identify which modem, in this case, our microcontroller that's broadcasting out these public keys, it will help you identify which modem it's coming from. And to get rid of the limit on bit length, this is what, for example, we'll start with just all zeros for a public key to make it easy to see what's changing. But in our packet format, you're changing, in this case, 1 byte at a time, and there's sort of this natural ordering where you don't need an ID for which chunk of data this is, because only one chunk of data is changing at a time, and you have this natural ordering. And then once you fill up this entire payload of 26 bytes, which is how much room we have for you to put your message, you can just wrap around. And again, the natural ordering is kind of preserved here, and you can continue wrapping around as many times as possible, or as many times as you want, so that you can have almost like an unlimited amount of data that you can send. Now, we also introduce this concept of chunk sizes, where you can change how much data is being added in each new packet to accommodate different situations. So here we have a chunk size of n equals 8 bits, so 1 byte of information is changing with each new packet. You can see the difference here, it's just 1 byte. This means that if you have a set amount of data, say if we were to use all 26 bytes and we had 26 bytes of data that we wanted to send, you would need to send out 26 packets now. But on the other end, this will mean there's less computation on the desktop side to decode it. And this is useful for areas with high traffic where you know that there's going to be a lot of iPhones that will pick up your messages, so you don't have to worry about people missing the packets. There's a lot of devices that would be able to ferry the packets for you. On the other side, you can make the chunk size as big as like the 26 bytes that we have for the data. And so here the chunk size is 208 bits, the full 26 bytes. And this is useful in situations where, for example, if there was only, you're in an isolated location, there was only one iPhone that was going to pass by per day for some reason, and you needed to get all your data out at once. You only have one shot to get your data out. You need to make sure that this iPhone gets it, and it's only passing you for a few seconds. So you want to send all your data at one time. This does mean on the decoding side that it will take longer. There will be more computation involved to decode it. But again, in a situation like this where you only have one chance to get your data out, this is very useful. And so between those two extremes, you can change the chunk size depending on your needs. If you know you're going to have in a busy location where a lot of people can carry your packets for you, you can use a smaller chunk size, especially also if you want to reduce the decoding computation. But if you're in an isolated location, you can use a higher chunk size. And kind of putting some numbers to this, we did some measurements just from chunk size of 1 bit to 8 bits, but the trend you can continue on. So on the x-axis, we have the chunk size. On the y-axis, we have the time to calculate possible keys, which is the biggest bottleneck on the decoding side. And you can see that it's exponential. As you increase the chunk size, there's an exponential amount of more time that you'll have to spend calculating these public keys to decode it. And additionally, one of our other contributions was having more efficient usage of the BLE advertisement packet. So instead of here, where we only have, instead of the send-my version, where you only have 1 byte used for the data, which is only actually transmitting 1 bit of data, and then all these other counters, padding zeros that are not being used, we have 26 bytes for the payload, and then we have 2 bytes for the counter value. And what this means is, with send-my, originally they had an original broadcasting speed of about 3 bytes per second. Through our measurements, we found with a chunk size of n equals 8 bits, so a byte, we were getting 12.5 bytes per second, and then the theoretical maximum, if you were to use the entire 26 bytes, would be 325 bytes per second. And so one of the drawbacks of this system is that there are no acknowledgements. There's no way to tell that, I broadcast out this Bluetooth message and someone got it on the other end. You can't tell that just from the microcontroller broadcasting out the packets itself. So it's and this is also true of Find My normal functionality. The AirTags are broadcasting out these Bluetooth packets, but there's no way for them to verify that they actually were received or picked up. So this is not just unique to TagAlong. But this means that the throughput is really important. So we wanted to measure the throughput to make sure that we're broadcasting out all these packets. We want to make sure that they're actually being received on the other end. So we set up some measurement experiments. We had 2 situations where, in each case, our microcontroller was broadcasting out 1,000 unique packets, and We would then see how many made it to the other end where we could decode them. In one situation, we had a single device picking up the packets, and then another situation, we were in a busy location with 20 to 30 devices who were picking up the packets. And again, this is to kind of show the two situations where you're either in an isolated location or a more busy location. And so we see that the top row is for the isolated location, only one iPhone picking it up. So, and then we also did different trials where we sent each packet 1 time, each packet 2 times, and each packet 5 times. And on the top row, you can see that, you know, when you're sending it 1 time with one iPhone, the data reception rate is very low. And as you send it more times, you know, there's increased chances that the iPhone will pick it up, but there is an upper bound to that. As you see when you send it 5 times, eventually, since there's only one device doing all this processing, you're gonna overwhelm the device, and so you get limited returns the more times you send the packet. But on the other hand, in the busy location, there's, you know, all these devices that can handle the packets for you, so the more you send it, the higher chance you have of someone actually picking it up. So we can see that when you're sending it 5 times, the best data reception rate that we got was 94.7%. And so in summary, we present TagAlong, which allows for arbitrary data transmission over Apple's Find My protocol. There's no infrastructure needed to deploy. It uses instead the existing iPhones around you to ferry the data for you. And we achieved a measured 12 byte per second data output rate with up to 97% data reception. And this is kind of a diagram of how the system works. But does anyone have any questions? Thanks.
Any questions?
So I was wondering if, you know, say this is something that takes off and Apple doesn't want you using their service for this, is there an easy way for them to change the protocol to block this, or would that require like replacing how existing AirTags works? And so is it sort of locked in how AirTags already do things?
Yeah. So there's kind of 2 parts to your question. The first part is we wanted this to be kind of a proof of concept to show that with the existing infrastructure, the existing distribution of iPhones, the existing way that Find My is done, it's possible to provide useful data transmission. So we don't want like people to actually be using our ESP32s and, you know, using this network without Apple's consent, but just to kind of to show that, like, you know, if Apple were to implement this themselves, it's a useful thing. And to your other question, they do not have, for example, when we are, let's go back. When we are querying the server, you send here, like the public key, and you can send a list as long as you want. And we were sending, due to the way that the TagAlong works, we were sending hundreds, probably hundreds of thousands total of requests, and we were never rate limited or anything. So, I mean, Apple could implement a rate limit there to discourage that. But besides that, one of the reasons that this works is the fact that because the Bluetooth advertisement packets, I believe it has 32 bytes for your payload, and the public keys that are coming from the AirTags are 28 bytes, and the other bytes are used for, you know, some like battery information and stuff like that. There's no room to include any sort of signature or authentication that says this actually came from an Apple device. So as long as the iPhones pick up this Bluetooth packet, and it's like the Bluetooth packet that we're sending out, and it's in the correct format, the iPhones will just process it like normal. So that is kind of built into, here, this packet format. That's kind of built into Find My as it is. It was meant as a privacy feature, but they would, yeah, have to rehaul the way that Find My works if they wanted to, for example, have authentication that it's actually coming from a proper AirTag and not just from like our microcontroller.
Thanks a lot.
Yeah, thank you.
Hi, thanks for the talk and the presentation. My question is, if you have to agree in advance with the receiver on what type of encoding you're doing, how many bytes you're encoding inside the packet, is that something that you have to agree in advance? And if not, how does the receiver know, you know, how many bits you encoded?
Okay, yeah. So this is something you have to agree in advance. It's kind of the same setup where when you initially pair an AirTag, just like a normal functional AirTag, there is that initial like key exchange that happens. And so that would just kind of be something that happens in the same situation, where if we're using TagAlong, you know, agreeing on the chunk size in advance and doing the key exchange is just something that happens the first time you pair it, and then you can go and like deploy the microcontrollers.
So then, to go to kind of my follow-up question, which was, you mentioned these 2 scenarios, like the busy and the kind of remote scenario. So this is something that you need to anticipate.
Yes,
before you deploy things, right?
Yeah, it would affect like the chunk size that you choose. It would still work, you know, at any chunk size, but there are chunk sizes, for example, if it was in the remote location where you would want to try to get out as much data as possible in one go. So yeah, kind of knowing what environment you're going to be in would be useful to know beforehand.
But there's no way to do it dynamically.
You could go and you would have to go back to the sensors and like redeploy it.
Okay, thanks.
Okay, I'm Jan. Thank you very much. And yeah, so okay, so you will the ESP32 wears like an AirTag, right? And it will like broadcast the data over the air, right?
Mm-hmm.
So do you have any limitation regarding the distance? Because you said that it's kind of like more efficient compared with BOE, but like in which perspective that you suppose that it's kind of more efficient compared with the BOE, like bandwidth, like distance or something?
The TagAlong is also using BLE, so you know this just works in normal BLE range as it would for the AirTag. The comparison was more about the prior work Senmai, where they had changed the public key to encode just a single bit of data, and so that was all of those changes were just based on the packet format and how much more data we were able to pack into the same packet with TagAlong.
So I thought I have answered this question with you before, okay, so we have like one AirTag, right? So one, like for your demos, kind of like one ESP, right? So it will communicate directly with a phone, right? So
It's not necessarily directly, it's just broadcasting out over Bluetooth, so anyone could pick it up, any phone could pick it up, but it's not necessarily direct.
What happens if, like, you know, sometimes you can have a lot of iPhone, right? But cannot reach the AirTag. But do you want to, like, here talk about, like, we will try to build it like a network, like a mesh network to, so, for example, like, you will try to reach, or it can reach the outrank iPhone, and the intermediate AirTag in between can do the job, like relay the message or something.
So it would be from like one iPhone to the AirTag to another iPhone, or
Like,
from like.
I'm not sure how AirTag works, but like when you have an AirTag, right? So it cannot reach a group of iPhone here. So it will work like you will have like another AirTag in between to help you to relay the information that you want to transmit from the AirTag to a group of iPhone or kinds of outrank devices.
Theoretically, you could do that. If it's just like, for example, here we're using ESP32 as a general microcontroller, you could just have them, you know, passing messages over Bluetooth, and then eventually it will get to an iPhone, and that will ferry it back. But the way it works right now is just, you know, waiting for the Apple devices to pass by, and just if it's not in range, then it won't be in range.
Okay, I got it. Thank you very much.
Yeah, thank you.
So if we have no more questions, let's thank the speaker again. Thanks, Carl.